So yeah, thank you very much, Jamir and Jairo, for the introduction and for putting together what really looks like a fantastic broad event indeed, as Jamir said. Yeah, let me start right away in view of the chairman's reminder of Aufpasse and start right away with the talk. So before that, I would still like to thank my collaborators, Ori Alberton and Michael Buchholder on the first project, and again, Michael Buchholder and this gentleman on the second main part of this talk. So Michael is really the one who's driving this project line ahead here. To begin the conference, maybe it's appropriate to really start again from the very basics. So let me remind you of the existence of two types of fundamentally distinct quantum dynamics. Of course, we have deterministic Schrödinger evolution in the game, but there's also a stochastic evolution type in quantum mechanics, which surfaces or which happens whenever you observe a system. In that case, the wave function collapses into one of the eigenstates of the observable, of the operator that you're actually measuring, and that brings in a stochastic element into quantum evolution. Now, this evolution is particularly interesting when the Hamiltonian operator generating the deterministic evolution and the measurement operator do not commute. Imagine the system collapses into a measurement eigenstate, the Hamiltonian doesn't commute, so wants to kick the system out of that eigenstate, and the wave function will ever happily evolve in time under such competing dynamics. But such a competition of operators is actually a scenario that in the many-body context is quite familiar. Again, very basic, a scenario of a quantum phase transition occurs whenever you have two parts of a Hamiltonian which do not commute and which each by themselves stabilize a qualitatively distinct ground state of matter. Yeah, one beautiful example is the Mott insulator superfluid transition, for example, implemented in cold atoms. Now, what is on the agenda today is to essentially
I think we lost sound. Am I right?
Yes, we lost sound.
Yeah.
But I think it's you and me, maybe.
I think Sebastian. I think
Sebastian
there's too many things open in his laptop.
It's a perfect way to open.
Yeah, yes, no problem.
It's a measurement, right? He was talking about.
I think he collapsed into
being projected
somewhere else.
He was measured and collapsed as he promised.
Yeah.
Also fairly.
As with anything, like any workshops, of course, that there's an issue with technical. With this.
Oh, Sebastian is back. Sebastian is back.
Okay, so Sebastian, I think you collapsed into a different wave function.
He's back.
Yeah, he's back again. Unmute yourself, please.
Someone is in the piercing.
I think you may want to not use that pointer. Just use the normal pointer.
Yeah. So does it work like that?
Yeah, that works very well.
On the measurement track, very good. So, okay, let's pick up quickly. So here, such a dynamics realizes a competition. Yeah, for example, which you realize when you look at the competition ratio, which is the number of measurements per times versus over the number of unitaries per time. Yeah, in the limiting cases, you get a crystal clear picture then. For example, when there's no measurements at all, these random circuits follow a chaotic dynamics, which means that there's a volume law growth of the entanglement entropy in the system. Conversely, if you have only measurements in your system, the state is projected onto a product state. That means a completely unentangled state, and that surfaces in this 1+1 dimensional setting as an area law in entanglement growth. So no growth at all. Now, what these works have demonstrated is that there is a true phase transition at a finite competition ratio between such a volume law phase and an area law entanglement phase. And that's quite an active subject where various physical pictures have actually been put forward to understand more deeply this beautiful phenomenon. Now, in this talk, I would like to introduce a little bit a model a little different from this random unitary circuit, something that is more motivated from real systems, namely a monitored fermion chain, in this chain, a numerical analysis has shown we've shown that there is an entanglement, a new type of entanglement transition from a sub-extensive logarithmic scaling to an area law, so not volume to area, but log law to area law. And then the main part of the talk is concerned with actually developing an effective field theory for capturing transitions of this type, including in particular the one that we discussed previously numerically. So so this brings me directly to the model. So we look at not at strong projective measurements, but rather at what is called weak continuous measurements, which are described by such an equation. The state update here is generated by a Hamiltonian generator of dynamics and this measurement evolution, where the random element of measurement evolution is signaled here by this variable being a random stochastic update, random stochastic Gaussian variable. Now, the competition is between this Hamiltonian and the measurement scales, and the Hamiltonian is just chosen as a simple hopping Hamiltonian on a one-dimensional lattice, as you can see here. And if you just look at the entanglement evolution under such a purely unitary dynamics, you find a volume law. Now, let's move to the other extreme and study this part of dynamics. Here, the measurement operators just determine the local particle density of the fermions, and there's this subtraction of the expectation value, which may look unfamiliar, but if you think about it, what that does for you is describing a continuous collapse of the wave function. So if you wait for long enough, then the system, in the absence of a Hamiltonian, will actually approach one of the eigenstates of this measurement operator, as in the projective case, just it's going slowly. Now, in that case, if there's no Hamiltonian, then clearly we also end up in a pure state with an area law entanglement entropy, no entanglement. Now, if we want to explore, and of course we want to, the entire competition axis here, then there is the caveat to take in mind that this psi, even including in the infinite temporal limit in the steady state, is a random variable. And so to extract information from that, you have to come up with some statistical analysis. And here is an important point in this business. The usual observables in quantum mechanics, they are these quantum averages here. But if there is a stochastic element, you have to do a statistical averaging procedure. Yeah? Usual quantum mechanical observables are going as described here. So you can write it as a trace of the operator with this state projector here. In particular, it's a linear in the state. That's quantum mechanics as usual. The problem in the measurement context with Hermitian measurement operators is that the average that enters here is always an infinite temperature structureless state. So essentially all interesting quantum mechanical information is entirely erased. Now, what to do about that? The trick is to use instead state dependent observables. Yeah? So some function of the state itself has a chance to indicate or to preserve some interesting quantum physics. Very simply, by this argument here, a function of an average for nonlinear functions is not the same as the average of a function. And examples of that include, in particular, that's probably why this von Neumann entropy is such a good signature. This is a highly nonlinear function of the state. Yeah? It involves arbitrarily high powers of the state projector here, but you can do actually it much cheaper and just look at observable state-dependent things that are quadratic in the state projector, such as this correlation function here. Okay, and that brings us in our model to this phase diagram. So this axis here describes the competition between measurement and hopping. And this axis here is 1 over system size. So the most interesting axis is down here in the thermodynamic limit. So what we see here is a phase transition between a phase with a sub-extensive, so logarithmic scaling of the entanglement entropy, which transits at a sharp transition point into an area law. So this here is a critical phase. There's no scale that would restrict the scaling of this function here, just it doesn't go extensively. And a further important feature to remark is this one, that if you look at the system at two small sizes, yeah, then it looks like a volume law. And so there's a crossover from a volume law to this asymptotic logarithmic growth, and that rationalizes also why the purely no measurement dynamics here, it persists really up to arbitrarily large system size, but it's an isolated point in parameter space that there's a volume law scaling, it's immediately gone when you switch on the slightest measurement rate. Now, here I will go quickly characterizing this weak monitoring phase. For example, this signature here confirms or tells you that there is an emergent conformal symmetry in this problem. Here, this plot can be taken as a determination of the critical point measured by what is called the effective central charge. So it's a fitting of the averaged entanglement to this function here, which assumes already conformal scaling. And this parameter here drops by orders of magnitude, really precisely at this at a well-defined point, already reminding a little bit of a BKT type transition. We'll get back to that. I would also like to point out that there is other diagnostics to such transitions than just the entanglement entropy. For example, this quadratic connected correlation function, quadratic in the state, is just as good an indicator for all the distinct scaling regimes in this problem. For example, in particular, I have this interesting 1/L square scaling, this extended critical phase, and the constant or the exponential decay of this correlator in this other area here. Okay, so let's now move to a deeper understanding of such transitions, yeah, with somehow having this example always as a guideline in mind. And I would also like to remark that there's a related work more focusing on these random circuits by Ehud and others that I guess possibly we'll hear about that later on.
Sebastian,
yeah,
so there is a question from the Q&A, which I will moderate in this case. They are asking if von Neumann entanglement entropy is a good metric to quantify entanglement when you consider mixed states. If you can quickly comment on that, because you have still 6 minutes before the end.
Yeah, I mean, right. So for these mixed states, all we do really is build on pure states, and we're doing this average in the end. For mixed states, you have to come up with other signatures, entanglement, negativity. So there's then other measures to be considered. Yeah? So why it works in our case is that we are evolving pure state wave functions all the time, and then we do the average only in the end.
Please go ahead. There are still 6 minutes or something like that.
Okay. Yeah, I'll try. Okay, so here is a basic picture for this transition, which we can see by just looking on one fermion on two sides. Yeah? So it can hop around and it's measured. So we're looking at the occupation locally. So if if there's no competition, the system will end up in either there is a fermion or no fermion. Now, if we switch on a little bit of monitoring, then you see this kind of dynamics here. The system is pinned to the measurement eigenstates for most of the time. And that is qualitatively different from this weak monitoring regime where we essentially are following here the Rabi oscillations, and there's only a vanishing time spent in the eigenstates. Despite these somehow qualitatively looking differences, nothing is visible in the linear averages, as I said, but it's seen actually in this quadratic correlator, for example, in this quadratic covariance matrix. And that is then giving us a guiding picture for the practical approach, namely, in the thermodynamic limit, we can expect just by taking infinitely many particles that there is really a sharp transition point between these qualitatively distinct looking regimes. So therefore we move to a minimal continuum model in 1+1 dimensions. And we also infer from that the state that this phenomenon could be unraveled in state dependent observables. So to this end, we do a replica construction. And the main insight is that these replica degrees of freedom that we have to introduce to get state-dependent observables host actually a non-Hermitian Sine-Gordon model, which indeed then models or shows that there's a pinning transition in the BKT universality class. So here are a few details. So we start with a fermion model, massless Dirac fermions. So that's like a naive continuum limit of this lattice model we looked at previously. And we can switch also to a boson variant of this problem where we have phase and density fluctuations. For the measurement, we measure the current and the vertex operator in the fermion theory, which translates into these kind of linear gapless density fluctuations measured in the boson language, plus this kind of nonlinear function of the density, which already tells you that this system, the measurements want to pin the system into the minima of this cosine. Also, you can see the competition. These operators do not commute with the phase part of this evolution here. Now, let's move to the replicas. So we want to access the state-dependent observables like this covariance matrix. To this end, if it's only quadratic in this state, we can just introduce two replicas. And then the physics is encoded in the average, in the linear statistical average of this replicated state projector here. Now, the evolution of this object has an interesting structure. It consists of two copies of ordinary Lindblad evolutions, but there is an interesting coupling term between these different replicas. And the key to making progress in this problem for us was to introduce new coordinates, new variables for this problem, which is an average coordinate over the replicas and relative replica fluctuations. If you rewrite the master equation in these coordinates, it becomes separable, and the average coordinate heats up to infinite temperature. So these statements are exact for Gaussian states and more generally useful still. The absolute average coordinate heats up to infinite temperature, and the relative coordinate, very interestingly, cools down into a dark state. So if you go through this procedure, you can actually, again, use separability for this evolution to map the problem to an ordinary or to a non-Hermitian Schrödinger equation, but systematically, which cools into. Here is the Hamiltonian, the non-Hermitian Hamiltonian for this evolution. It consists of the Hamiltonian operator, of the measurements, and this here is the nonlinear effect of the measurements that we have to take into account. Now, the physics of this problem is evaluated in a path integral approach. So this is the action that features in this path integral. It can be brought to a standard kinetic term, and then there's a grain of salt. There is a purely imaginary nonlinearity. Looking at the RG flow of this theory, we see that the flow at short distances is modified from the standard KT scaling, so that gives us shifts in the phase border. But interestingly, in the infrared flow at long distances, we converge towards the standard Kosterlitz-Thouless flow. So therefore, the long wavelength physics must be in the Kosterlitz-Thouless kind of this reach. In particular, for the phase diagram, we then find a perfect algebraic decay, which all the time is 1 over x squared in line with numerics. This is what we understand as the depin phase in the Kosterlitz in this effective bosonic theory. And on that side here, we find exponential decay corresponding to a pin phase, where the measurement really pins the systems into eigenstates of the density operator. The phase transition by this argument is clearly in the BKT universality class, and in the meantime, we have really very strong numerical evidence that this is true. Now, finally,
1 minute.
Yeah, very good. Yeah, finally, we are interested in the entanglement entropies to make contact to the entanglement transition. Yeah, so there we have to go to n replicas simply for these reasons here. That's the definitions of the objects we're interested in. Interestingly, in this Keldysh approach, we find that for n replicas, one mode heats up, but n minus 1 modes still cool down. And we can actually show that the calculation of these entropies or the von Neumann entropy including can be done as for ground states, with the result that we see an area scaling in this regime, subvolume log law in this regime. And there is, and even we get the, so to say, this point here right as a non-commuting limit. So that underpins this entanglement transition also in this approach. So that's the conclusion and outlook. And maybe to get the discussion going only very quickly. Yeah, so at the moment we are thinking about how can one observe such things here in experiments, for example, using homodyne detection. We're looking for other incarnations of this measurement-induced transitions, where in particular we're looking at these long-range hopping models, where we can find an extremely good agreement between our analytical theory and this and numerics, and we find a particular a new kind of phase transition to a new algebraic sub-extensive scaling law. And we are also looking at the other competition patterns where we force the system to go into an entangled state via dissipation, put it into competition with a boring kind of Hamiltonian, and that gives us kind of a dual scenario with really exactly the same phenomenology. So I think there's still a few things to be discovered here. And with this, I'm happy to take your questions. Thank you for your attention.